Welcome back, everyone. So let's continue on in chapter 21 and talk about the chemistry of esters. These also can undergo nucleophilic acyl substitution reactions. And one of the main reactions that esters can undergo is hydrolysis, which means, and the word hydrolysis, by the way, if I'm not incorrect, comes from two Greek roots, meaning loosening by water. And so that's exactly what we're going to do. And esters can certainly be hydrolyzed in acid or in base, thus necessitating different mechanisms for both of these cases, both of which will need to make sense given the pH of the solution. So here, as an example, let's just take ethyl benzoate. I could have picked any ester, and let's consider what the mechanism would look like in acidic solution. So here, we're simply going to heat up the ester, probably heat it up, in dilute aqueous acid. So now we're not talking just a bit of acid catalyst. Here we're going to have a significant amount of water, which is essentially going to wind up being the reaction solvent. And so that means that we can invoke water molecules. In fact, we will, as you'll see very shortly. We can invoke water molecules, we can invoke hydronium ions, and that's about it. There's not really going to be anything else. Truthfully, the dilute aqueous acid, it could be some dilute aqueous HCl, maybe some dilute aqueous sulfuric acid or phosphoric acid. The identity of the acid doesn't really matter because it's going to be a strong acid, which means it's going to dissociate, right? It's going to dissolve in water to produce hydronium ions plus anions of whatever the conjugate base of that really strong acid is. Could be the bisulfate ion, HSO4- if we use sulfuric acid, could be chloride ions if we're using HCl, but be that as it may, whether bisulfate or chloride or any other anion, they're not going to play a role in the reaction. Those are going to be spectator ions. They're terrible bases, and they're not going to be used as bases, not when there's anything that's a superior base around. And water would certainly be a far superior base than either of those two particular examples, or really the conjugate base of any strong acid. So since we're in acidic medium, we need to be careful to protonate our acid carbonyl oxygen first. And again, remember, we need to show where the proton is coming from, not just write H+. I commiserate because Owl and the textbook are both quite a bit sloppy at times, but we're always going to specify where that proton comes from, because knowing that is part of understanding the reaction. And so in dilute aqueous acid, our acidic species is going to be the hydronium ion. So we'll use that to put the proton onto the carbonyl oxygen. Again, that's not something memorized beforehand. That's something that we observe and make a decision about at the time we face the problem. Good, so once we've done that, now we can have our nucleophile attack that carbonyl carbon. And again, our nucleophile needs to make sense. We're not going to use a hydroxide ion here, OH-. Why not? Because the problem, as it's stated, clearly states that we're an acidic medium, and you're not going to have any hydroxide ions in an acidic medium. Certainly not in any reasonable concentration. Anything near high enough to be used in the mechanism. So even though the result of this step will put a plus charge on this oxygen, which is true, at the same time, after we do this step, we'll get rid of the plus charge on this oxygen. So going from the species with a +1 charge to another species with a +1 charge isn't really a problem. So that being said, as is so often the case in reactions in acidic medium, we now need to do a couple proton transfers. These are all going to be separate steps, and they're all going to be intermolecular, not intramolecular. There's no way we can shorten this and say, put this proton straight on that oxygen. I think you'll find if you try to do that, you'll wind up with a 4-membered transition state. And that's not a low energy pathway at all. 4-member transition states do happen, but if there's any better way of getting the step done, even if that means using separate intermolecular steps, that will be much preferred. There's certainly no shortage of water around. Our H3O plus solution is going to consist mostly of water with some certain concentration, maybe 0.1 molar, maybe 0.5 molar, who knows, but some concentration of H3O plus ions in there. Good, so we'll use a water molecule, once again, not hydroxide, a water molecule to pull off this proton and get rid of the plus charge on that oxygen. Now we basically have the hydrate of the ester. And so then we also need to put a proton on the alkoxy group, in this case ethoxy, so that we can lose that as a molecule of a neutral alcohol. And we don't want to be losing something like ethoxide or methoxide or any other alkoxide ion in the acidic medium. That does not make sense in acid. Those species are way too basic. And the way you can know that, remember, is by the pKa of the conjugate acid. So the conjugate acid of an alkoxide is an alcohol. Alcohols of pKa's of what? In the upper teens. And certainly if we're sitting here at a pH of 1 or 2, we're nowhere near a reasonable pH that we can invoke having alkoxide ions present. If we were at pH 14, maybe, then we're getting much closer to the pK of the alcohol, and one could imagine having some alkoxide ions present. But at an acidic pH, no way. And again, remember, you have to know that in order to understand this. It's simply not going to come by memorizing, not in my experience. Okay, enough of that. So we put the proton on again using the hydronium ion, and now we're able to lose this alcohol molecule as a leaving group. And so the result when we do that is essentially our protonated carboxylic acid. You simply invoke a water molecule to pull off the proton and give us that carboxylic acid molecule. So that's how ester hydrolysis would look in acidic solution. And to me, again, it always seems like the mechanism is steppier in an acidic solution. It seems more straightforward in the basic solution. Let's take a look at that. So let's now hydrolyze this ester. We'll call that methyl hexanoate in a basic solution. And so what we're going to need to do is treat the ester in aqueous base. Could use sodium or potassium hydroxide or any similar hydroxide salt like that. But then remember, we're going to need to do an acidic workup because we're going to wind up with, at the end, with a carboxylate ion. And so we need to put that proton back on. More on that step when we get there. Now notice, since we're an alkaline medium, strongly basic anions are perfectly fine to use in our mechanism. And so, as so often happens in basic medium, our first step here is bombs away. Our nucleophile attacks our carbonyl carbon and forms an oxyanion, which is fine because we're in a basic medium. In acidic medium, no way. But in basic medium, this is just fine. Then, again, very much simpler in alkaline medium. Now this oxyanion can simply collapse and kick out the alkoxide ion, whatever it might be. In this case, it's methoxide, but simply kick out that alkoxide ion as a leaving group. That's okay in alkaline solution. And depending on what the problem asks you to put, especially keep an eye on OWL. Sometimes they'll require separate sketchers, etc. But if you need to account for how the alcohol is then formed, well, it's going to come by protonating this alkoxide ion with a molecule of water. Water is slightly more acidic, by generally an order of magnitude or so, than most alcohols. So I think this equilibrium will favor formation of the alcohol in another hydroxide ion. And then the other piece that we form is this carboxylic acid. And even though that's the product that we're trying to get, remember, we've just formed this carboxylic acid molecule in alkaline medium. And so we cannot prevent that deprotonation from occurring. There's no way that we can add acid soon enough to prevent us from having to show this deprotonation here. Because if we try to do that, then what we'd wind up doing is neutralizing the base before a significant amount of reaction has happened, and we'll get a product mixture. So the reason that we have to show this is because we've generated an acidic molecule in the presence of base. And so we have to show this step. You can't stop this step from happening. And we've seen this before. We've seen phenols and carboxylic acids both being formed in an alkaline solution. And so we need to show the deprotonation with the base that's already present to give the conjugate base of that carboxylic acid or the carboxylate ion. And that's what's going to be swimming around quite happily in our reaction vessel until we add the acid to work up the reaction. Remember how numbered step reactions work. Remember that what this implies is we're going to add aqueous base to our ester and may or may not heat it. It certainly wouldn't do any harm to heat it, at least gently. But in any case, we're going to add the ester to aqueous base, and we're going to wait until everything is done reacting, until all of the ester is converted all the way through to this carboxylate ion, and then we will add aqueous acid. The first action of the aqueous acid, of course, will be to neutralize any leftover base, hydroxide in this case. And then the hydronium ions will start protonating our carboxylate ion to generate the free carboxylic acid. So this is how saponification or basic hydrolysis of esters happen. We also mentioned that briefly, although not with the mechanism, in chapter 27, since we were talking about soaps and how they were made. So that's a pretty good place to stop also, I think. Let's save amides and nitriles for another lecture. Probably will be a fairly brief one, but there's nothing wrong with that. So have a good day, and we'll see you all later.